So when in here, in Buffalo, you typically will see this as a solid red. If this is solid red, you are not allowed to turn left. But if it's a flashing red, you are allowed to turn left. All right? So you see a flashing red, then you can turn left. Okay, so that's very quick. I think today's lecture probably will be finished very soon. But now is the third topic. The third topic today is about pedestrian simulation. And this is a very big topic. If we want, we probably can spend 4 or 5 lectures to talk about it. In today's lecture, I'm not going to do it. I just want to watch a video with you. And before we watch this video, let me first introduce one thing. In this paper, in this video, the authors are presenting a new methodology to simulate the pedestrian movement. And they present a new thing called navigation field. So you know electronic field, you know magnetic field. And they use this kind of navigation field to guide the pedestrians. And this is different from the traditional agent-based model. In an agent-based model, each pedestrian will only consider itself. And that will lead to big problem when we model a lot of pedestrians. In their methodology, they are going to use a field, and this will be the trace, and the arrows in each cell will represent the strength and the direction of the field at that point. And this paper is going to be published on IEEE transactions, on visualization and computer graphics. So let's first watch this video together. And when you are watching this video, don't pay too much attention to the technical details, but think about why we need it and when do we need it. Let me repeat. The question will be, when do we need to simulate pedestrians? Okay, let's watch this together.
This scenario shows a subway station with people entering and exiting the station. We use a local collision avoidance mechanism based on reciprocal velocity obstacles with a naive global path planner for this particular simulation. Please note that the simple agent-based models operate in a local scope, resulting in congestion at the turnstiles. Such behavior is clearly undesirable. We allow the user to direct the simulation using a simple sketch-based interface. The agents are partitioned into 6 groups according to their common objective or destination. We allow the user to quickly sketch the intended direction of movement through the turnstiles. The user also edits the trajectories of agents at a group level to reduce congestion and get better macroscopic behavior. Our approach allows the user to specify realistic crowd flows to control the flow of agents through the turnstiles and achieve the desired macroscopic behavior. Our method works in conjunction with simple agent-based models. Its use is independent of the choice of local collision avoidance schemes used, and it allows the user to edit the simulation at runtime. Here is a schematic overview of our approach. There are several possible modes of user input. The user can choose to interactively sketch the desired trajectories, or could import flow fields extracted from crowd footage for more realistic simulation. A naive combination of the guidance fields with the pre-existing global path planner could result in the occurrence of singularities, and convergence to the goal cannot be guaranteed. Our key contribution lies in seamlessly compositing arbitrary user input with a goal-directed plan to generate singularity-free navigation fields for global navigation. This scenario is comprised of 4 groups of 25 agents in each corner of the environment, whose goals lie in the opposite corner. In the middle, there are 4 square obstacles that form narrow passageways. Traditional agent-based models, which plan for each agent independently, lead to congestion in the center of the environment. To resolve the problems with the earlier simulation, the user specifies a single global circular flow that guides the agents to their respective goals. The simulation on the left shows how a naive combination of the user-specified guidance field with a roadmap-based global path planner cannot ensure convergence to the goal. In contrast, the simulation on the right shows how our approach constructs a singularity-free navigation field that guarantees that the agents reach their goals. This simulation indicates how our approach allows the user to edit the simulation at the group level. Here, the user specifies trajectories independently for each group of agents. These trajectories combine with the global planner to create unique crowd flows through the environment. This scenario shows 4 streams of agents meeting at a crossing. It is a well-known fact observed in real crowds that this particular configuration results in the formation of a vortex at the center. Traditional agent-based models are not necessarily able to replicate this particular emergent phenomenon. Our approach allows the user to emulate such emergent phenomena, such as vortex formation and formation of lanes, even in simple agent-based models, to generate more plausible behavior. This simulation shows a group of agents moving through a corridor. The width of the user-drawn stroke is specified at runtime and allows the user to effectively control the dispersion of agents along the trajectory. This simulation shows pedestrians crossing at a regular crosswalk. Our method allows the user to edit the simulation in a variety of ways. In this particular example, flow fields are extracted from actual footage of pedestrians at a crosswalk. The user can then import these flow fields into the crowd simulation framework to generate more realistic behavior. This is also an important step towards data-driven crowd simulation. Extracting the flow information from videos is a difficult problem, and the resultant guidance skills are often sparse and noisy. This data can be used in conjunction with the sketch-based framework to generate desired behaviors.
Okay, so that's the end of the video. I'm pretty sure that you don't understand the detail. But for my questions, I want you to discuss, to present your answers. So the first question will be, why do we simulate pedestrians? Could you give me some good reasons? Now's the time to think. We see some examples of simulating pedestrians. Why? Why do we need to do it? Anyone has any creative answer or just normal answer?
If we want to design an exit in a subway,
Yes.
we need to simulate pedestrian behavior first and choose the correct location for that exit.
Good, that's a very good point. That's for designing buildings, subway stations, or shopping malls. We need this. So any further reason?
Maybe near a football stadium or something. When the game lets out, it'll have effects on traffic.
So it's like evacuation, emergency evacuation plan. So that's a very good point. Good. Anyone has any other answers? There will be a third answer, which is not related to traffic engineering, but it's for game or movie development. In that cases, you want to develop more realistic movement of these pedestrians or units or agents. So these are the good reasons that we want to simulate pedestrians. Very good. Now, second question. What do you think will be the difference between a pedestrian and a vehicle? They are different, of course, but how are they different from each other?
Vehicles are rational, pedestrians are irrational.
Vehicles are rational. Why is the vehicle rational? Vehicle is driven by human
We follow the
rules, because there are some traffic rules. There are signal constraints, restrictions. Yes, you're right. So vehicles are controlled by some well accepted rules. That's a good point. So is there any other difference?
There are the lanes for vehicles, but they are
not lanes. Yes, for vehicles, they have to drive on lanes. So, and that's why we have a lateral movement modeled as lane changing, and longitudinal movements modeled as car following. So basically they are traveling along the lanes, but pedestrians have more freedom. Any other difference? So the third difference will be the magnitude of speed. The vehicles can travel as very fast or very slowly, but the pedestrians are of almost the same speed. So these are the differences. Very good points. Now the third question. Let's suppose we have a simulation model of pedestrians, like the model we just saw. How can we calibrate it or validate it? What data can we use to calibrate that? Or what methodology? So in car following model, we can use the time-space diagram to calibrate it. In lane changing model, we can calibrate using the capacities or anything else. But for pedestrian simulation, as you see, they are moving on a 2D plane, which means we cannot using a 2D time-space diagram to calibrate it. If we want, we can use a 3D time-space diagram, but that can hardly be seen, can hardly be presented. So we can, if we consider each pedestrian as a point, we can use the contour map or density map. They are very similar to calibrate it. Contour map or point density map. Or we can use the capacity of the facility or the level of service of the facility. For the capacity, we just mean how many pedestrians can pass through the facility at a certain amount of time. Level of service can be represented by the density or the average travel time of each pedestrian. So these are good things to calibrate the pedestrian simulation model. In the simulation tools we introduced, there are 3 that have already implemented or have some. There are 3 tools that have pedestrian models. The first one is MSOM. MSOM has a model which is developed by another company called Legion. So if you want to do some research about MSOM's model, just search Legion's model. For Visim, it has another well-known model called social force model. So the interactions are modeled by the force between individuals, pedestrians. And the third thing is Ceramics. Ceramics modeler itself doesn't model pedestrian, but it has another tool called Urban Analytical Framework, UAF, which employs a myriad tool model. So if you want to do some research about the pedestrian models, use these 3 of them. Check out the literature of them. Coursing or Transims doesn't have these. So if, let's say you want to simulate pedestrians in Transims, you probably have to create a certain vehicle named pedestrian and apply some logic to it. And I want to emphasize that for the traffic signal thing, I didn't introduce to you how to use the software to model the traffic signals because I don't have much time left. But you can check the manual. If you understand the basic concepts, then I think you have no problem to understand it. So today's lecture is very short, and it's the end. And Thursday's class is canceled. And there will be only 1 class left on next Tuesday or Thursday. I haven't decided yet. And on that lecture, I'm going to talk about the plugins, which is